Good evening and good morning. This is a joint seminar webinar series 2025 by NTU-CIA and UIUC-CDA. So let me introduce the first speaker today. The first speaker will be Professor Dr. Wu, assistant professor in the Department of Biomechatronics Engineering. Her research interests include development of optomechatronic systems for applications in agriculture and biotechnology. In addition, her research groups combine several AI-based image analysis technologies and with optomechatronic systems to automatically monitor cells, plants, and further reconstruct the 3D cells and plants. Let's welcome Dr. Wu.
Okay, thank you. Good evening in UIUC and good morning in Taiwan. So my name is Hsiao-Mei from Department of Biomechatronics Engineering at National Taiwan University. I'm honored to give a talk in this small agriculture in crop series. Today, my talk is phenotyping the plant response to abiotic stress by the fluorescent lifetime imaging systems. Okay, so here is my outline. I was starting to introduce my lab, bioelectronics lab, and start today's talk about starting from the motivation and background why I'm doing this one, and introduce a little bit principle of my technique, FD3. Then talk about the breakthrough we made and experimental design, following the results and conclusions. Okay, this is a research area in our lab, just like Professor Huang just introduced. My lab mainly is developed a optomechatronic system to apply in biological, biomedical application and agriculture application. So today I'm going to focus on the upper top region, the right-hand side, the green part, the fluorescent lifetime, fluorescent imaging, and the 3D phenotyping applying the small agricultures. Okay, here's the motivation for my today's talk. So as we know, climate change is making extreme weather events such as heat waves, prolonged droughts, and erratic rainfall. Seriously, they give crop production a very serious pressure. So especially water storage disrupt the key plant function like photosynthesis and nutrition transport. So therefore, we are the real-time monitoring of the photosynthesis efficiency of plants under various stresses are very important, and it's very important for small agriculture. So that's why we want to develop this. However, according to the survey conducted until 2020, among a lot of technologies are widely applied to agricultures in developed country. Unfortunately, photosynthesis efficiency sensors are still lowest adoptions. Only 5% in developed country and nearly zero for the developing countries. So how do we detect the photosynthesis efficiencies? Here is some background for everybody. Light energy absorbed by the chlorophyll molecules there in a leaf, there will have three paths possibly to happen. First one is driven the photosynthesis in photochemistry and provide the sugar and energy to the plants, live plants to grow. Second possibility is here is dissipated as a heat energy. And third one is re-emitted as a fluorescence, chlorophyll fluorescence. Therefore, measuring this is three possibility: fluorescence, heat, and energy for the plants will competition to each other. So if we measure the fluorescence chlorophyll fluorescence, we can estimate the possibly to estimate the photosynthesis efficiency. Traditionally, people will measure the fluorescent chlorophyll fluorescent intensity. As you can using the ratiometric method to estimate the photosynthesis efficiency. As you can see, author Wang in 2018 already integrated this fluorescent intensity measurement together with other optical system to do the high throughput monitoring. And here is their result on the tomato leaves. The leaves is under drawn test in the day 5. We can see that you can already see the significant difference for the water stress from the fluorescent intensity measurement. Recently in Washington University, they published a paper in 2021. They measure the chlorophyll fluorescent lifetime and using a time domain method. Then their sample is called the Venus minor. They treat the plants for the freezing test for -20 degrees and -78 degrees for different duration, for 2 minutes, 5 minutes, and 10 minutes. So let's zoom in to see their result. The upper bar, the upper figure B is the result measured from the fluorescent intensity. And the bottom 1D is the result measured from the fluorescent lifetime. There are 3 experimental set. For every experimental set, the left column is leave under fluorescent test for 2 minutes, 5 minutes, and 10 minutes. The right side column is the control experiment. So from these 2 figures, we can clearly show that despite the fluorescent intensity-based imaging is almost unstable, and to discriminate what happened to the leaf, the fluorescent lifetime has higher sensitivity to can detect the damage of the leaf. Why is it? It's because the nature of the fluorescent intensity and the lifetime. The advantage of measuring fluorescent intensity is because it's simple and inexpensive experimental setup. However, the result, as I mentioned before, is ratiometrics, so it's a quantitatively observation, and it's very sensitive to the background. So you will have lower sensitivity. On the other hand, fluorescent lifetime, because it's only sensitive to the parameter, only sensitive to the structural change of the probe. So it can be a quantitative measurement, absolutely measurement. And it's independent to your experimental cell which has a higher sensitivity. And but it needs an expensive experimental setup, and it has a limited probe. Fortunately, in our case, for chlorophyll fluorescence can have autofluorescence, so we don't have to worry about the indicator problem. So how do we measure the fluorescent lifetime? I already persuaded you that the fluorescent lifetime has a more higher sensitivity. And how do we measure it? There are 2 major ways. Till now, most people are using the left-hand side, most straightforward way is called the time domain measurement. All in these 2 figures, green curve means the excitation curve, and the red curve means the emission curve. For the time in the time domain, we will give a pulse excitation, and the laser and the emission curve will have an exponential decay curve. Through theoretical principle, we can find the estimated lifetime from this decay curve. Unfortunately, the lifetime we are measuring for the chlorophyll fluorescence is within 1 or 2 nanoseconds, which means that our pulse laser has to be at least picosecond level or even faster. And acquisition photo detector should be even has the same speed. That will be very challenging to electronics device. So traditional ways of people are using giving a lot of pulse on the same sample and then gradually accumulate this decay curve, and then we find the estimated lifetime. But as you can imagine, a lot of pulse on your sample, the sample could be damaged very easily. So that's why we want to use the frequency domain one to measure the fluorescence lifetime. In this way, we will modulate our excitation like us in a sinusoidal way. And we can attain the same frequency, but with different amplitude and with a phase shift emission curve. From this amplitude difference and also the phase difference, we can estimate the lifetime. So summary about these two methods, time domain can give us a better signal to noise ratio, especially if our sample have a weak signal. But the drawback is that the pulse data is very expensive. And the other drawback is that we can damage our leaf easily after a lot of excited light dose. For the frequency domain one, we can have a very fast acquisition speed and you don't have to damage your sample, can do the lifetime measurement. But the drawback is that if the light dose is very low, photo counts will give us a very poor performance. So as we mentioned, there are two ways to measure the fluorescence lifetime from the frequency domain. One is from the modulation depth. It's about the amplitude of your emission curve. So it's more relative to intensity-based one because you are treating the amplitude is very important for your estimation variable. The other way is using a phase difference to estimate the lifetime. We call this as phase lifetime. If you use the amplitude, we call it modulation lifetime. And both lifetime we can plot into like first plot called a phase plot. Okay, so we set out our experiments in this. So we give in sinusoidal curve to our 470 nanometer LED light source and use a 610 nanometer long pass filter to do the as an emission filter and consider our signals to do the final lifetime estimate. To make sure our modulation frequency is in a stable high frequencies, we use a silicon photodiode amplifier to monitor it. Okay, so why we are talking about the frequency modulation frequencies? Because in a phasor plot, for different modulation frequency, we can have a different resolution. Particularly for few nanosecond resolution in different modulation frequency, the resolution sensitivity depends on your modulation frequency. So here is the modulation result for 1 megahertz, 5 megahertz, 10 megahertz, and 20 up to 30 megahertz. This is a breakthrough we did here. We successfully modulate our LED up to 30 megahertz, and then people still provide very good and uniform illumination for us to the measurement. And in this way, can give us a very high, reasonable and sensitive result. Okay, so here's our experimental setup. We choose beef stick tomato as our sample. It's because the tomato according to FAO in 2024, tomatoes ranked as the most produced vegetable product globally. So that's why we choose this one as our sample. And two major tests we are doing. For each specimen, we sandwich it between the two slides. And for lifetime measurement, we choose 5 different spots to do the FD link measurement. So two sets of experiment we are doing. One is you put the leaf in the oven for 50 degrees for 1 hour is simulate the extreme accurate drum test. The other is no watering test. So the tomato plants will keep without irrigation for 1 week. So every day we will choose one leaf from 2 to 4 branches for, to do the experiment. Here is a typical result we have for the lifetime measurement. You can clearly see that the facer part, we have a very good spot indicating the results very local and very clearly. Also, you can see very clearly sinusoidal excitation and emission curves. So for our result, here is the open test result. The left-hand side group is the lifetime estimate from the modulation. That's from the amplitude. Estimate the lifetime. It's more related to intensity measurement. And the right-hand side group is from the phase difference to estimate the lifetime. You can see that for every figure, the left-hand side is the control experiment. And the right-hand side is the leaves already under the oven treatment for the 1 hour. Okay, we can clearly see that the phase lifetime can give us a very significant difference, unlike the modulation lifetime. So which means that indeed from the phase measurement, the lifetime can give us a more sensitivity expected results. Also, this is the same result plot in the violin plot. We can see that clearly for after drying for 1 hour, the phase lifetime has a significant tidally distributed and a much lower distribution compared to the modulation lifetime. We also compared our result to literature. Here is a the imaging after in the microscope. So the upper is the fresh leaves. It shows that the leaves are under uniform brightness and clear structure. On the other hand, the leaf after dry treatment reduce the intensity and the structural collapse and uneven brightness. This result is the same as the Dr. Brewer's published in 2010 shows that the plants reflect physiological heterogeneous and fluorescent lifetime will vary with the local cellular environments. And this is the second result for the no watering test. The left-hand side also is a result from modulation lifetime, and the right-hand side is a phase lifetime. You can see that in the first 4 days, the modulation lifetime almost gave us a very stable result, consistent to the previous result we showed for the no watering for tomato plants. We can only detect the result after the day 5. Similarly, phase lifetime will have significant difference in the after day 5, but still can has slightly tell the lifetime difference in the first 4 days. So the result of also we can see that more clearly result if we plot in the violin plot. So we believe that this system can support the rule for fluorescent lifetime can be an early indicator of stress. And this result consistent with the previous literature who emphasize that lifetime sensitivity to microenvironment environmental changes. So we further use this device to measure the root oxygen concentration in plant root. And we found that under aeration increase the oxygen concentration along the plant primary root compared to the oxygen without aeration experiment. Besides, we try to use the fun bar and also the RGBD camera and chlorophyll in image system to compare to each other to combine the result from phenotyping result combined to the photosynthesis efficiency estimation. And those following two experiment is under the progresses. So to a conclusion, in this study, we developed a frequency domain fluorescent lifetime image microscopy called the FD Flame system. So the system has a potential for detecting physiological change in a non-invasive and relative sensitive approaches. And two tests we have already done. One is a drone test, the other is a no watering experiment. For the drone treatment, the fluorescent lifetime parameters, particularly phase lifetime, were reduced and show a broader distribution. And this is reflecting that decreased photosynthesis efficiency and increased physiological heterogeneity among cells. In the non-water experiment, fluorescent lifetime remains stable for the modulation result. We can hardly tell anything in the early stage, but the phase lifetime can give us some results. And it shows that lifetime change might occur before visible symptoms of water stress. And we also show that our system has been useful to test the oxygen concentration of the plant root. And also we try to combine the chlorophyll fluorescent images and the 3D reconstruction from RGB images for better plant phenotyping in the future. So overall, the work demonstrates the feasibility of using FD flame for early stage plant water detection. So in the future, we plan to use this system to various environmental conditions. Okay. So this is my group. All these students work hard for our results and from the lower parts of my funding agencies. Thank you for your attention.
So thank you very much for Dr. Wu's speech. We would like to have any comments or questions from the participants from the United States. Any comments or questions?
Hello, this is Nicolas Martin. I would like to know, thank you so much for the presentation. I would like to know whether you are planning to use this approach to compare plants that are drought tolerant versus plants that are not. Do you have any plans for the future on that?
You mean future, the plan using for, could you say that again?
Yes. I mean, in future research, in future studies, are you planning to use this approach or technique for comparing drought tolerant plants?
For different plants, yes. We are doing that too. We are trying to drone test for different plants. Also, we want to use this technique for different nutrition or maybe the different temperature or light control. For everything can influence the photosynthesis efficiencies. That's our interest.
Thank you.
Thank you for your questions. And also we hope that this early detection can give us a chance that like for no watering test for 3 days after we give the put back the water, the chlorophyll, the photosynthesis efficiency can increasing after we put back the lower the water stress. That kind of thing. That's what we are going to do in the future. Thank you for your comments.
Okay, Dr. Wu, here we have one question from the NTU student, and the first one is there a big difference between the flower lifetime of leaves of different species?
Fluorescent lifetime, you mean the amount of the fluorescent chlorophyll fluorescent lifetime? It shouldn't be a lot of differences. Also within few nanoseconds, so 1 to 2. So it's more likely influenced by the structure change. So which means any stress on the plant that will change the molecular structure, then the lifetime can change. Okay.
Another question is how does drying affects the fluorescence lifetimes in plant samples, and what can these changes indicate about the plant's physiology's response to the stress?
So this test, we are doing this for a benchmark test is because it can give a accurate water test a very short time. So to test the system can real detect this kind of dynamic physiological change. So original plans that we are trying to do the different type, like the oven heat test for 10 minutes, 20 minutes, 30 minutes to see there will be gradually showing the system sensitivity. That's the plan for that. Okay. Thank you. Oh.
Okay, we still have time for the last question. If a farmer wants to install devices, use them to for related applications, how much would the cost of the equipment increases the production cost from the farmers?
Oh, this is because this is only development stage, so the cost may be not so low so far, and also it's we still under, you see the result here showing is still under the microscope, and but only the oxygen measurement is for the large view. So to better apply for the really farm application. So we need to enhance the LED intensity and also to lower down all the electronic cost. Yeah, so it's one way to go. Okay, is any other questions? Okay, so that's all. Thank you.
Professor Bullock, you can start to share your screen.
Okay.
Our next speaker, the second speaker is Dr. Bullock. He is a professor in the Department of Agricultural Consumer Economics at the University of Illinois. He studies the economics of agricultural technology and information. He is the PI of the USDA-sponsored data-intensive farm management project, which use precision agricultural technology to conduct large-scale experiments, which generate data to add farmer management of nitrogen, fertilizer, and other inputs.
Thank you.
Let's welcome Dr. Bullock.
So here are the main points I want to make in my talk. The first thing is that something we call on-farm precision experimentation is revolutionizing agronomic research and bringing that research straight to the farmers' own farms and away from perhaps away from university fields. That the second point is that farmers and crop advisors can work with the data-intensive farm management projects directly to run these trials. And that those experiments create great data from which farmers can improve management of those same fields they're running the trials on. And finally, this is all done through a user-friendly platform at DIFM.farm, which we call a cyber infrastructure. All right. If you take a first-year university course in economics or agricultural economics, you'll see this picture, this graph in the first month. And what it is, it's a graph that shows the technological relationship between an input X and an output Y. And that curve, that function is called a production function. Or in agronomy, it's often called a yield response function. And in that class, you'll learn a little piece of microeconomic theory. If you were 17 years old and I was giving a lecture, I'd spend 45 minutes explaining the intuition behind this theory. But really, you can show this in a few seconds with a little bit of calculus. And it's that if the profit maximizing amount of an input depends on the price of the input and the price of the output. And the economically optimal choice is to find the place on the yield response function where the slope is equal to the ratio of the input price to the output price. All right. What they don't tell you in that econ course, or at least nobody told me, was that nobody knows what this function looks like, especially for agriculture and especially under different growing conditions. Because agriculture, crop agriculture, has so many variables, types of soils, types of weather, it can be very hard to take from data what the relationship of input to output are, because there's so many other variables involved. All right, so that means that the key challenge to precision agriculture, okay, is to understand how different parts of a farm field, okay, how yield on different parts of a farm field respond differently to an input in different years. Here I've assumed that this field has 4 different management areas, A, B, C, and D, and those are determined by what yield response looks like here to N, which is nitrogen, fertilizer, in particular years. So the point of precision agriculture and the challenge is that in general, we do not know what this picture looks like. And so even though we have brilliant engineering that hooks tractors up to satellites, and you can use computer programs to try to put different amounts of an input in different places, really nobody knows very much about how to vary inputs in different places to make more money. We just don't know what this picture looks like. All right. Another interesting fact, the person who invented statistics, what we learn as basically the science of statistics, modern statistics, was a guy named R.E. Fisher. And the data he was working with was the exact same kind of data that we're talking about today, which is field trial data. R.A. Fisher worked at a agricultural research station in England in the early 20th century. And he's been called a genius who almost single-handedly created the foundations for modern statistical science. So what I'm saying here is that this problem of learning how yields respond to inputs is ancient, and it's very important. And that's clear by how much work people have put into it. Okay, this is how Fisher's small plot trials work. Here you see a drone shot of a place which is 21 plots, each about 10 meters by 4 meters in size, in dimension. And here there are 7 different nitrogen application rates from 0 to 24 gallons per acre. And different rates, what can happen is you can find a place where 0 nitrogen was applied, and you can find a yield, and that gives you a point of data. You can find a place where 24 gallons was applied, and that will give you a yield. And if you do that 21 times, you get 21 observations, and you might learn something about how yield responds to that input. So these are small plot trials. People have done thousands and thousands and thousands of these, and they have been doing them since even the 1700s. Here's a copy of a article in a book where an English gentleman farmer was running experiments, seeing how changes in manure rates change output of barley, change barley yields. So this is an ancient question that people have known as important for a very long time. All right. Agronomists get a huge part of their data from these small plot trials. Thousands are run in the public and private sector every year. Okay. The thing about small plot trials is that they're expensive. To create small plot trials, often scientists have to go out with measuring tapes and orange flags, and a lot of research assistants and technicians, and maybe some small machinery, but a lot of inputs are put in by hand. And as a result, it's expensive. Okay. And the reason small plot trials are small is because they are labor intensive and therefore expensive. You can't afford to hire enough labor to put a huge trial on an entire field. Okay. And the problem with them being small is then all you really learn about is how yield responds to an input on a small part of a field, maybe something the size of 2 basketball courts, instead of thinking about the real question, which is how does yield response differ over large parts of land? All right. Want to switch gears, precision agricultural technology. When I was a young man in the 1990s, first starting to discover precision agriculture and do research on precision agriculture, I saw a lot of pictures like this in magazines, maybe a little bit on the early internet, where people thought that they were going to farm by the meter. They're gonna run a tractor through a field, and in different places they're going to do different things, and that's going to be something that's very doable. That is actually not the case. It is much harder than this picture makes it look. And to a large extent, a lot of aspects of precision agricultural technology have not met up to the promises that that people supposed they would meet, a generation ago. These days, the big thing, the buzzword is big data, agricultural big data. People say, well, we can fly drones across fields and take pictures, or we can fly satellites and get all kinds of petabytes of data, or we can just do all sorts of things and use sensors and learn all about data. And therefore, we have agricultural big data, and therefore, if we can just put all this data together, we can help farmers farm better. I'm going to maintain that that's really not how it works, that it is not sufficient to get a bunch of drone data and satellite data and things like that. And the reason is because if you want to learn how to manage better, you need data that shows changes in management. Okay. If you don't show it with data what happens to yield when you change management, all the drone pictures in the world are not going to help you. All right. So here's my point here. If our data looks like this, so there's not much variance in nitrogen in this picture. There's not much variance because we didn't actually run an experiment. We just let farmers do what they usually do. Then you're not going to be able to figure out how the yield response relationship is different, say, in a sandy part of the field compared to a silty part of the field. In other words, you cannot fit curves through columns of data. And because you can't fit curves through columns of data, unless you run field trials to go with all the different kinds of sensor data and satellite imagery, unless you also run trials, I maintain that none of that data is worth a whole lot. All right. All right. So this is why we run field trials. We run field trials so that we can get data that's variant enough that we can fit curves and find out the relationships we're trying to find out. All right. The take home, and this is really important, is that you don't, if you don't get data that comes from different management options, you won't know what happens when you try different management options. In other words, the data is not going to help you manage better. All right. Okay, here's a different idea. On-farm precision experimentation. OFPE uses precision technology to generate data needed to estimate the site-specific yield responses. OFPEs are way bigger, way cheaper, and implemented by farmers on their own fields to get information about how to manage those same fields. All right. The data intensive farm management project, which is the project I work on, it runs these FPEs with farmers and crop management advisors to get these kinds of data. Okay, here is an example of some data that can be gotten from an on-farm precision experimentation. This is a field from Ohio, which is in the Midwest United States. And this is a 71-acre field, so it's about a 30-hectare field. And on this 30-hectare field, what we've done is we've created a shapefile, a file that partitions the field into hundreds of plots. And each one of these plots has one of 5 nitrogen application rates. And so we are varying these plots, just as in a small plot trial, we're varying the application rates, except we're doing it on a very large field. Over here in the red, this is a map of the as applied data. So the machine, when it went through the field, it used GPS and variable rate applicator, and it applied the design onto the field. And so these are actual data as applied data. And you can see clearly that the dark red matches up with the shade of red matches up with the shade of gray. In other words, we can put an experiment like this down on a field. What you see over here on the right is yield. It's a yield map. And so the yield data shows clearly that there was a response to nitrogen. You can see places where there was low amounts of nitrogen supplied in the light red. Then there is low amounts of yield here in the light brown. Okay, what's that mean? We are doing this, the Data Intensive Farm Management Project, and the team is based in many, many universities in the United States. Here you see scientists at, I don't know, probably more than 20 US land-grant universities. We also have working with a bunch of people in Quebec. We're also working with people in South Africa and Brazil and Ukraine. So this is a worldwide project. Okay. And this year we're going to run about 100 trials, which is great. That's much more data than people have been able to get in the past. But we don't want to run 100 trials. We want to run tens of thousands of trials each year. And we want to get data from tens of thousands of trials each year. We think that will really make a big difference in how much we learn about how yields respond to the inputs and other things they respond to. To make this possible, to run tens of thousands of trials per year, we have developed something we call the DIFM.farm infrastructure, cyber infrastructure. And I'll tell you how that works in a second. All right, to run this OFPE, what you do is you create a shapefile that is just a file of polygons, and each of these polygons has a number assigned to it. And then the farmer can bring that trial design into his monitor on his applicator, and the applicator will put that amount of nitrogen down. So here is an example this is a seed rate trial, and one of our farmers took a video with his iPhone of his planting monitor screen as he was planting. Because his steering was locked in with GPS, he could take this take this video and still drive straight. What this shows in the yellow is that the planter is trying to plant seeds at 30,000 seeds per acre. In the red, it's the as planted rate. This is the actual amount being planted, and you can see that it's a little short. It's planting seeds at approximately 29.65 thousand seeds per acre. When I show you and I turn this on, you'll see this bounce around, and after a few seconds, this will change from 30,000 seeds per acre as the targeted rate to 42,000 seeds per acre. And soon thereafter, you'll see this 29 and 30 jump up towards 42. So you see the target rate is 30, as applied rate is 29, 30. Target rate goes up to 42, and very soon the applied rate goes up to 39, 40, 47. All right. So what this means is that this is easy for the farmers. Okay. Farmers use this equipment all the time. And so they can run these experiments without orange flags, without a lot of technicians, with a lot of labor. These are easy to put in the ground and they're inexpensive to put in the ground. All right. At harvest, of course, we can use yield monitors, and the harvester can record what the yields are as it goes through the fields. Okay. Here's a video made by one of our farmers.
This is a short video of my brother harvesting the soybean population study on Wente Farms Ltd. You can see the combine moving across the field with the population maps in the background. Isn't technology great?
Okay. This cyber infrastructure that I'm talking about is available. You are welcome to go to difm.farm and you can look at it, you can access it, you can play with it. It's free to the public. Let me show you a piece of that. Okay. If I go to difm.farm, okay, I can come to this web page. I'm already signed in, but if you wanted to, you could create your own account and sign in. I might be a crop consultant that has many farms that I work with. One of those farms might be, let me see which one I want to use. This one. And here, if I want to, I can create trials. Okay. And when I create trials, I can put in different numbers here. And in just a matter of minutes, okay, I can have this computer make field trials for me. Okay. Much more than that. And that only takes a few minutes. It's a very user-friendly way to operate things. Okay. What this also does is what this also does is let me see if I can find this. It enables the farmer to not only create trials, but generate reports that describe the data that was created, that process the data, that analyze the data, and that write reports. Now, in this short amount of time, of course, I can't show you all this, but we meet regularly, and I'd be happy to go over this in much more detail with you to show how this works. All right. So with this DFNUP farm, anyone can create field trial design shapefiles. They can get help putting these trials in the ground. They can upload, process, and manage the data, and they can use statistical and artificial intelligence analysis to think about the real-world management implications of the data. All right. What we end up being able to do then is to think about how in different parts of the field, different application rates. Here it's a seed trial. Work better than others depending on the part of the field. You can see here that on the western part of the field, where there's high elevation, the most profitable seed rate is the highest seed rate. But in the central part of the field, the orange here, medium elevation, the most profitable one is much lower. What this enables us to do is to provide estimates of optimal planting rates to the farmers who are doing these experiments. And so all of a sudden we can provide them data-based information about how to manage different parts of the field differently. This is free. We are making this free to the world. which is why people in many countries are starting to use this. We have gotten over $9 million in grants from the United States Department of Agriculture and other sources. We think we're putting them to good use. All right. Data security and ownership. Any farmer that works with us, they own the data. We don't sell the data. The data is secure. It's based on the Oracle Cloud. So we feel like the data is very secure. Now, this technology, of course, is maybe not for Taiwan. It's not for places with small fields and small farms. It's for places like Ukraine, Brazil, Canada, United States, Argentina, Australia, where there are big fields that have big equipment that have precision technology. But from this technology, a great deal can be learned, and I think that we are beginning to generate data that has never been generated before. Thank you very much.
Thanks for your wonderful presentation. Any questions from the participants in the United States?
Yeah, this is John Reed. Thanks, David, for a great presentation. I'm curious about as you learn these functions for a field, what has been your experiences of what the farmers do in subsequent years? Are they able to use these to drive their application rates or seeding rates and get a direct return, or is it some other changes that take place over time? What have you been experience there?
Often, yes. Often, one thing that is very clear is that, especially in parts of the western corn and soy belt where it doesn't get as much rain as the eastern soy belt, the seed rates are often too high. Farmers are planting corn and soybeans often at higher, in other words, they're listening to their seed sellers, their seed dealers. And so we have been able to convince, well, we don't convince anybody. Several farmers have cut back on their seed rates because they can see that in a lot of years, the seed rates are too high. So that's one example. Another thing we're learning is that, say with nitrogen fertilizer, as you know, there's a lot of problems with water quality when nitrogen fertilizer goes down the Mississippi River into the Gulf of Mexico. It creates environmental problems. There's been a lot of talk that this was happening because farmers used more nitrogen than they needed to maximize profits. Our results are finding that it doesn't look like that's really true. It's true in some instances, but it's not generally true. That has policy implications, which means we're not going to fix the nitrogen problem simply by showing farmers that they can make more money by putting on less nitrogen. You're going to have government policies. You're going to have government policies that help farmers manage their nitrogen fertilizer better. So those are just a couple examples. So yes, farmers pay attention. Now, of course, 1 year of data is very much dependent on the weather, right? And so if you have a different weather, the results are going to be different in another year. This is why it takes time. We're creating a system where farmers can do trials, not every field every year, but in many fields in many years, and start to be able to use the data and understand probabilities and how their decisions, the probabilities of the results of their decisions. Farmers are gamblers. We think we can use this system to help make them better gamblers, but we can't take the uncertainty away.
Okay.
Right.
Here we have one question from the NTU student.
Mm-hmm.
And the NTU student, I would like to ask whether older farmers are willing to use the smart system composed of GPS and the agricultural machinery.
Yes, they are. It depends on the farmer, of course. And it's true that often we'll tend to work with the sons and not the fathers, because it's easier to get young people to want to use this kind of equipment. On the other hand, a lot of this technology has been around for a generation. So even the farmers who are in their 60s, they encountered this technology and started using it when they were in their 30s. So this has been around a long time. It just hasn't been made to a large extent. It's been underused. It's been used a lot, but not to very good effect. So yes, a lot of U.S. farmers are already used to this. Even if they're old, they were doing it 30 years ago. This is not new technology. What's new is using this technology to gather data.
So thank you very much. Thanks for your presentation. And let's move to the third speaker.
Thank you very much.
You. Our third speaker, Dr. Chen, is an associate professor in the departments of biomechatronics engineering at NTU. She earned her PhD in agricultural and biological engineering from the University of Illinois Urbana-Champaign. Dr. Chen's research specializes in application of image processing and spectral analysis techniques for plant status monitoring and agricultural product quality evaluation. Her work is centered on the advancement of smart agriculture through integration of IoT and AI technologies to enhance precision farming methodologies. Let's welcome.
Thank you, Professor Huang. It's my honor to be here to share our research data with you. And today I'm going to majorly focus on using the AI-driven image analysis in the smart agriculture, especially to enhance like the crop monitoring and until the quality prediction. So in my lab group, we're using the machine vision to do lots of different tasks through the whole supply chain from the farm to the market. So we do like for the plant management to see how the plant grows, is it healthy or not, and is it reach the harvestable stage or not. And for the after harvesting, we also do some grading for the post-harvest process. Not only just use like a RGB image, we also use like a hyperspectral image to detect those abnormal situations that we cannot see by the RGB images. So today I'm going to share several case studies with you. Majorly will be focused on the plant disease identification, and also another one is to do like some small robot to do the automatically scouting job for the greenhouse asparagus. So start with plant disease identification. Plant disease identification actually is a hot topic around the world. So for many of the research groups develop their own plant disease identification tools for different crops. The reason is we plant those crops, but they will still happen or like affected by the plant, like a pest or like a disease. However, we cannot get access or like ask question to the plant doctors all the time. So we can use these tools to help the farmer to have like an in-time diagnosis, and then probably they can do an in-time strategy to prevent the production loss. So here we are not only just to identify which is which and then give them like the result, also to combine with like the follow-up, the prescription suggestion. The major crops that we do this study, there are several crops we are targeted to. One is the tea tea is an important economy crops in Taiwan. And another one is like a cucumber is a vegetable crops. So for build up these two systems, in the very beginning, we need to collect lots of images from the real field to develop the disease database. So for both database, we collect more than 5,000 images, and then we use like the RCNN-based models to do the identification for the object detection. And for those things, we can achieve around like more than like 80% mean average precision. For those farmers, then we apply or like we implement those methods by deploy that to the Line app, similar to WhatsApp, like in Europe or like in America. So this one is very simple to use. The farmer just upload an image, and then the image will send this data to our server, and our server will do the identification and send it back the result to the farmer, and they can click the result, and then will direct them to the suggestion pages to give them like a follow-up suggestion from the government. So that's the first stage system development. Second stage is we are not only just do for the identification, we also do is like the follow-up prescription, because once the farmer knows like what happened to their crops, they want to know then what should I take the action for next step. If there is a plant doctor, then plant doctor will give them some suggestion like you may take like removal, or like you may use this type of biological material to do the prevention, or like to avoid further spreading like that. So we kind of mimic this logic from the plant doctor, and also to kind of like collect a lot of information from the government and also from the expert and develop this system. So this system give an advantage, especially when the farmer faces the pest or disease, multiple pest or disease happen at once. Because this system will list all the applicable drugs together, but put the common drugs for multiple disease first. And then they also will list the safety period based on the shorter period first. Not only for that, we also had like expert recommendation. That one is not just limited to the chemical way to do the prevention, also include the other type like a cultivation or like a biological control. This allows other farmers taking like organic farming or like eco-friendly farming, they can still have some information what they can do based on this. So before we introduce like two types of crops. One is tea and another is cucumber. And we also do that for other variety of vegetable crops, especially for the urban agriculture. This one is majorly to develop for educational purpose, because for urban agriculture, some of the farmers are not professional farmers. They are just the general users, like maybe your neighbors, they have like a small scale farming on their rooftop, or like elementary school students, they have like their practice in their campus like that. But when they grow their plants, they still will see something happen to their plant, but they don't know what happens and what to do next. So that's the original idea to develop the vegetable crops in the urban agriculture. So this one we focus more for like the general user, and also emphasize on the educational purpose. And so for the treatment itself, the suggestion will based on eco-friendly, like physical one, or like organic material. So here we have 8 types of vegetable crops, and also like 3 types of the disease or like a pest. Depends on like if we see the bug or not, or like it's pest invention or like a disease infected. So same thing as like the tea apps. Here we also developed the vegetable apps for the users. But different things is here we can see all the suggestions are based on like a biological control material. Not only for that, we want to get some improvement for our plant disease identification. So we try to do more. Before we only use like the image information to do the diagnosis. And now we are thinking what we can do more. Probably we can add more by asking the user to type in some informations. Then we can build the image and also text multi-model identification model. What will be the advantage? First, if the user cannot get very clear photos, then they can help by providing a more clear description. And second, some environmental factor won't be catched by the image, such as like the temperature, season, or location. So those are not included in the image, but could be included in the text that the user provided. So we utilize those features together. So for now, we're still under development, but for the preliminary result, we can see if we only use like an image-only model, we can get the precision around 85%. But once we add like the text into the system to do the multi-model one, we can at least to boost up the performance by 5%. So that's like what we do. But before we talk about we using image data to do that, but this only limited to those we still can see the feature, the symptom by our eyes. Those are visible symptoms. However, when we see the visible symptom, sometimes it's already hit the middle stage or late stage. So some of the farmer or like the plant professions will say, could you do better? Could you identify them in even earlier stage? But it's very tough to using like an RGB image. But the hyperspectral image can do that for us because hyperspectral image can give us the image, but also provide the spectrum information. So for that one, we can have a very rich information, and the spectrum information will give us the composition change, even we cannot see that from our eyes. So for this study, we select the brown blight disease in tea because this one is a major cause for Taiwan tea production loss. To do this one, so we can see, usually when we see a green leaf, we will think it's a healthy leaf. However, if the green leaf located in a disease plant, then it's still being infected. But if we only use the RGB image, then we won't know. So let's see what the hyperspectral image can do. Because we want to document the disease progression. So we just to inoculate the leaf by the pathogen, we force those leaves to be infected by ourselves. And then we keep to record those data for a week long. So we can know how it progressed. And then we trying to categorize it into 4 types. One is totally healthy one, and another 3 will be different level of infection. Depends on like for the injured one, it's very clear symptom that we can see for the dark spot, and for the injured like one is a region surrounding them, and then for the asymptomatic, just a regular green pixel, then looks exactly the same as the healthy samples, but it located in the infected leaf. So for that one, we can just using like a 2-day difference to identify which area is the injured-like one. And based on these 4 categories, we use like the 3 models to identify if we can classify them or not, especially for those 3 types. We see them in the green pixels. So the two model will be the fundamental machine learning model, the KNN and the random forest, and another one will be the 1D model. Obviously, the 1D model gives us a better result to reach above like 80% accuracy. So this result tells us, yes, we can apply the hyperspectral image to get early detection. So this one could be applied to the field test. Like we can use this one and then to nose like early stage infection for the brown blight for the pig farm. Okay, so we now shifting from the plant disease to the farm management right now, and then introduce a little bit like the farm robot, and we had a little bit experience for that one in the greenhouses. So here is a case in Taiwan asparagus cultivation situation. In Taiwan, the cultivation method is quite different from those methods in Europe or like in American, because of our temperature and also climate is different. For the US or like European, usually only grows spear, the asparagus that are eatable. But in Taiwan, because our climate is more humid and hot, so we have to adapt another type of like a cultivation called smaller stalk cultivation. So we can see the scenario looks quite different for the mother stalk cultivation, because it includes the mother stalk itself and also the spear. The whole scenario become more complicated. So the farmers need to manage more, bring them a heavy load of like the farm task. And we all know now it's already hit like some severe situation. The situation is we are short of like the farm labor, and also for all the farm population are very old. So the automatic tool are very important for them, can save their time, save their labor, and also their load. So that's the ideas. If we can just trying to develop like some small robot for them to do the auto scouting for the field. So that's the idea. So we start to build this small robot to do the scouting job. This robot equipped with like a 3 camera. One is a front view camera to do the guiding things, like the front view. Then we can use that to guide our vehicles by themselves. And for the 2 side view camera will collect the plant growth condition. Here is a asparagus growth condition. And because the scenario here is really complicated, we still need to identify which is a stalk, which is a spear. Yeah, so the task become even more complicated, but the new AI image processing is quite powerful. So it helps us to do this job, especially for the transformer model. It kind of a boost the recognition capability, outperform the previous like the RCN ones. So here we can see our model from the 2023 to 2024. In 2023, we will see something is not that ideal because we cannot get a complete object. But for the 2024 one, it looks much better. And then from the number, we also can see for both like a stalk and spear, we can get a higher, the MMP percentage higher than 90%. And then for second one is we expand our recognizable variety from the green asparagus to the purple asparagus. So this one is to try to include more variety and then to widen the application for the industry. So once we have the scouting robot and also had immediate analysis for that, we have to give those information to the farmers. So we build up the system website. The website had the function to give them to check what the robot acquired, and then also give them the identification result. And in the end, also give them the stat page. The stat page will show like the different object that be recognized. Like for the stove, the color will show different level of the density in different regions. So a little bit like a small scale of the phone map like that, like heat map in the phone. Once we have this map, then we know like the density map for the farm. And then we can use that to do a more precise application for irrigation, for fertilization, and also for pest control. So that one brings us then to collaborate with like some machinery company in Taiwan and then to develop the small pesticide spray robot like this. And here is some demonstration for the whole system. So this scouting robot can drive itself based on those sensors, like the front view camera and also LiDAR system. And then the side view to acquire the plant growth condition. And the website will show the location and then the photos located in that at that time. And the state page will show like how the distribution around this field. And in the end, we can apply those, utilize those density information to develop precision spraying robot and then give the variable rate instead of uniform application. So basically, I already introduced all the cases, then I would like to introduce for the image processing. But we are not only just using those spectroscopy technique and also the AI methods for image processing. We also use that for like the food processing and also for agricultural product quality, such as like the origin discrimination and also for the flavor prediction. But with limited time, I won't introduce it today. So with that, I would like to thank all the members in my lab to do a lot of work to build all the research results and all the funding agency and collaborative partners. So thank you for your listening. I will be happy to answer any question that you may have.
Any question or comments from the participants in the United States? Okay, maybe we can answer two questions from the NTU student. How does your plant disease identification system handle variation in lightning backgrounds or image quality in real-world field conditions?
Okay, that's a good question because we before we talk about we need to develop a database. A good quality database is very important. Light condition is a severe challenge in the open air condition. So we will, when we do the collecting job, we try to collect the image during different daytime, like in the morning, in the afternoon, cloudy day, sunny day. So that's what we try, just to include as many as possible the variations for that one. And then also like when we do the photo shooting, we also will allow like some angles range to taking the photos. So there will be some flexibility to fit in those photos. Yeah.
Okay, so the second question is that will the accuracy be affected by the lightning?
Yes. Yes, of course, yeah, it's affecting hugely by the lighting. So that's what we need to collect as many as possible during different daytime and different conditions. And sometimes it will also be shaded by other leaves because of the sunlight angles. So that also need to be considered when we do the data collection.
Hello, this is Nicolas from Illinois. Are there diseases that are easier to predict than others in your experience?
Thank you for your question, Dr. Martin. Some of them are easier to identify, some of them are very challenging. So we have the professional plant disease professions from different crops, like for the tea, we have the plant doctors to collaborate together with us, so we can get one choose from her. And for the cucumber and also for vegetable, also they have like a different professions to collaborate with, because like they all expert for different type of crops. And our student cannot learn that tips. So usually we still need to confirm this with those experts. Some of them are very different from each other. That one is more easy to be identified, but some of them are very similar to each other, and some of them are complex disease, like not only just one, maybe more, and then they will all each other. Yeah.
Thank you.
Thanks. Okay, thank you for. Okay, thanks for Dr. Chen's presentation. Thank you very much. So let's move to the fourth speaker. Dr. Martin, you can start to share your screen. Dr. Martin improves long-term profitability and stability of cropping systems by exploring application and of quantitative methods on big data. He leverages interdisciplinary efforts to expand the frontiers of agricultural researches. Investigates quantitative methods on processing at multiple spectral temporal scales. He studies effective approaches to implement new insights and discoveries in agricultural decision and operations. Let's welcome Dr. Martin.
Thank you. I was muted by accident. Thank you so much for the opportunity to discuss some of our work that we do here at Illinois. I work in spatial analytics. I am trained as an agronomist. I work on statistical analysis and how to integrate geospatial methods and analytics in the decision-making process that farmers do. So I work in a wide range of topics, but I wanted to focus on the idea that Professor Bullock was explaining early on. We did extensive research in this area, and here we are starting to address some of the questions that he was discussing early on. And I think the framework that we are conveying here can be expanded in a variety of bases, and I want to share and discuss that with you. So I want to begin by saying I like this picture that I created, because in a way what we are trying to do is to make experiments in a more creative way, I would say, than the small research plot trials we were trained to work with as agronomist and statistician. And this precision ag technology allow us to work that way and answer questions in a different way than before. So I wanted also to share some slides to more or less give you an overview on how the agricultural systems work in the US and the extent that they have. So here is Chicago, here is the Mississippi River, and basically here in this dot is where Urbana-Champaign is, and I could easily drive for about 12 hours and I will be here, and it will look pretty much the same if you come in July. And the reason is because all this area that you can see in green is cropland. Most of the time is corn and soybeans, sometimes wheat. And as a side effect, there is always a trade-off that farmers and agronomists wants to I will say balance, and it has to do with reducing cost, reducing impacts, and also maximizing profitability. So I will say nitrogen and seeds are the most expensive inputs the farmers apply, and also they have a tremendous impact on yield. And sometimes because of that, they rather sometimes over-apply or under-apply. But I think, I will say in the building I am working, I will say there are probably a couple of floors full of researchers working on some version of this topic. And also it connects with people. So this is a river close to where I used to live in Iowa. You can see through the water is clear. If you come, notice that there are no leaves. So this is like April over there. And if you come in August, this will be probably green with algae bloom. And part of that is fertilizer or either nitrogen or phosphorus that create algae blooms. As David indicated early on, this is not uniform. It doesn't happen all over at the same time. My impression from other research we have been running using other approaches is that there are like hotspots. It's not like an even problem, I would say. So if you happen to come and visit Champaign, or in this case is Bloomington, this is how it will look like right now. So the grass is turning green, but still crops are being planted as we speak. You can see that there are field patterns, right? Some areas here are a little bit lighter, others are darker. So sometimes there is rain and the water carries some topsoil, and you can see this different availability of nutrients because of that. So this field variability is very exciting. You can see also the dimensions. So every square that you see here, more or less this to this to this, is a 1 mile by 1 mile by 1 mile. So let me move to the next one. So if you happen that in reality you come and visit Champaign in August or early September when the classes start here, you will see something like this. And so you will see clearly field patterns. These areas here have corn, these ones here have soybeans, and you can see that there are spots. And these spots are, we assume that are areas that are dying sooner, they are senescing sooner because they lack water. Sometimes it might be diseases. But in some situations, you can see that that happens across crop. So it doesn't matter the crop that you are growing, these patterns happen anyway. And so then farmers for ages, I mean, since I will say 30 years ago, they have been trying to capitalize on this. So David show you these other pictures. This is the oldest I know that has this framework from, this is 1995, more or less. And again, the idea is to have different layers of information, soil information, maybe some sort of sensor information, and then applying different management practices on it. Some of these technologies have been widely adopted, but the application of nutrients hasn't. And even there has been companies working on that for a long time, and more recently as well. And in a way, the business model around trying to use these digital tools haven't been very successful, I would say. And the framework consists more or less on the following: is we want to measure soil conditions, look at soil variability, and fit different functions, more or less the way that Professor Bullock was showing. And according to that, then you can come up with different recommendations. So, and this is a framework that has been developed for that consists on, then you will have a yield response. So this is a yield map. And then it will depend on the soil conditions. So you can have a vector or a set of attributes that could be topographic, organic matter, other variables that are important related with the soil. You can have also information on how the weather conditions are behaving that season. And in this work, we are going to focus a little bit more on that. And then you have these kind of trials that David and the group at the DIFM have been developing over the years, right? So you will have something that looks like a checkerboard with different treatments. So, so before coming to Illinois, I was working in an industry setting, and they have more or less a chain of value, right? And you can even see some of that in some of the conversations you have been having throughout this seminar series. And normally, you can use technology or methods to create descriptive analysis and then conduct some sort of inference or conclusions from research. But then when you start adding predictions for specific places, it gets a lot more uncertain. And without that, this part of coming up with a recommendation becomes a lot more challenging. And I think that's related with the current challenge that we have for this type of technology. But I have seen it for other problems as well. So, so this framework also occurs this way. So, and again, the concept that people often use for defining these maps is called management zones. So then they define with different algorithms areas that have common attributes or characteristics, and then they assume that they will have a differential function. And by function, we mean differential responses to nitrogen as we apply them. So then the main question that we wanted to answer in our work is, are these management zones consistent in space and time? And also whether they are consistent by input type, right? So, so this work has been published in a couple of years ago now. And it is based on using these on-farm experiments. And so we compile about 20 sites. Mostly, they are all of them in Illinois. And what we wanted to identify is where the inputs are responding in different areas of the field. So that's a little bit on what we want to do. So what we want to know is the spatial variability and temporal consistency of the crop responses to controllable inputs. So the key contribution of these DIFM trials is that we can actually map or create maps where we see the impact of the crop responses to the inputs. And before this project, that wasn't quite possible at scale. And now we can look at how much spatial variability you observe on the responses and whether these responses are consistent across years. And then whether there are differences between inputs for the same year, okay? And more important, we want to know what are the factors associated with these responses. So in a way, we want to answer the key questions that were that was challenging for understanding these responses. So we will focus on then this aspect of the management, and then trying to map the impact of the management on the yield and see how the other variables are also impacting that. So this is our workflow in order to do this. So, and we're gonna navigate through some of them over the period of the analysis. So, so what we have here is, in a way, initially the maps where we have the DIFM trials set up, and then we also obtain the yield maps as well. And then, so we have information about the yield maps, about the input supplied, and then we try to aggregate the data in a consistent fashion. So then we have then all the data in the same footprint. And then we go and we conduct an analysis called geographically weighted regression. And what it does, and when we initially start working on this, that was probably the main or more intuitive approach. Now there is a wider variety of methods that can do the same. You can probably also do this with deep learning, for instance, and image analysis. And then, but the idea here for now, given that we were working with these functions, is to create regression functions in different areas of the field. So we can make maps of correlation and regression coefficients accordingly. So then once we have a map with the responses, we can see whether these responses are consistent or not. We can also look into what are sources of information that we can use to try to guess where these variables are taking place. So, okay. And so we did considerable amount of work in collecting topographic variables. We collected also daily weather data, and we have also information about soil maps and soil features. So I will say almost all this information is publicly available in the US. You can easily generate that, and it's information that many agronomists and service providers give or provide farmers for free. What it is not easily available is this. And then we start using some explainable machine learning methods to try to identify what are the variables that are important, and also the marginal impacts of individual variables. So this is a little bit on how these functions might look like. And then, so here we have 7 fields, all of them in Illinois. We have in each of them different years. So we have, for instance, in field 1, the year 2016 and 18, and in others we have 19 and 21, and so on. Notice that we have alternating years because of the annual rotation we have in the central Midwest with corn and soybeans. So here in 2017, we had soybeans. So that's why we are skipping that. Then we have then two different methods. One is ordinary least square. So it's a traditional regression function that we apply uniformly across the field. And then here we have the same for GWR, and this is for the two variables we are working with. So when we are designing these trials, we have a completely randomized design. Let me go back in this plot. So it's a completely randomized design, and we have combinations of seed and also combinations of nitrogen. So our models were trying to guess that arrangement. So let me go back a little bit here before I move on. So then, because of that, we have different regression coefficients. So we have areas of the field, for instance, that for field 1, we have negative responses to nitrogen, and in other areas, we have positive responses to nitrogen. And the same happens for seed rate. So we have areas of the field that have very positive responses. Some of them are negative. So, and this is also, in this field, it's clear that they probably were putting way too many seeds, maybe. And so this is an overview. And also notice that we have here quartile 1 and 3, and it's because we have a continuum where we have many responses, and we have areas of the field that respond a lot and others that do not do it so much. So we end up with maps like this. So this is for a given year in one of the fields. So we have areas in green here that have a negative response, areas in red that in this case is not responsive, and then areas of the field that have positive response. And this is for nitrogen, and this other example is for seed rate. Notice that the areas don't clearly overlap. So areas that respond to nitrogen are not the same ones that respond to seed rate. So some of you might be wondering whether there is interaction. We couldn't find significant interactions on this, at least in this type of trials with the type of range of treatments that we have. So to summarize and simplify the analysis, we combine the negative and not responsive, and we only focus on the areas that have a positive response to the inputs. So, and then what we did is saying, okay, we are going to see whether the areas that have a positive response are consistent or not. So this is the example, for instance, for nitrogen. So here we pick two fields. This map here that you see at the bottom corner is the same one you just saw a second ago. And notice that areas that respond to nitrogen, well, sometimes there is an overlap. So what happens is that because of that, it is hard to guess where these functions might work, right? So, and this is a similar situation for seed rate. So the seed rate map is that you see here is similar to the one you saw before, but simply combining the non-responsive and negative. And notice that year 1 and 2 complement each other in a way, almost. And then in some fields, we have better agreement for the positive responses, but in general is quite inconsistent sometimes for people to commit and say, okay, I go and I build my maps, and and then I find this area, and then 1 year it responds, the other doesn't. So then we start investigating with the DALEX package in R, basically trying to explain how these zones can be predicted using different soil variables and also weather attributes. So notice that clearly the variables that had the most impact were seasonal conditions. So whether you got rain at certain times of the year or not. And then landscape position, slope, and so on, or the shape of the field had some impact. Soil variables had some impact, but not much. And then the complementary variable, the alternative variable, had very little impact, relatively speaking. So, so I will say I wasn't that excited about this. I was hoping that it would be more consistent. So here we investigated a little bit more. We tried to identify precisely where the different breaking points take place. So here we have only seasonal information across the fields, basically. We noticed that, for instance, conditions in May have an impact for both of the inputs. Conditions in July had some impacts on nitrogen rate. But then I will say that July precipitation and June temperature changes had an impact in the response probability that you will have across these fields. This was really, really interesting. And so we're gonna go to this part. This part is the scary part. So, so here we have topographic variables in this case. And what we notice is the information that we have here is when you see something in color, is because that variable had an impact on how these maps were taking shape. But then if you can see, many of them are in gray. So, so A refers to nitrogen, B refers to seed rates. And for nitrogen, not many variables, relatively speaking, have an impact. So the different colors represent different fields. But think about the conclusions you can make. You cannot make generalizations from one field to the other very well. And I will say at best, what it will take is to have a very large data set with many, many fields and many years and seasons, have an idea on what are the patterns, what are the risks. And I think at the end of the conversation, Professor Bullock was explaining that pretty well. So these are some other characteristics that we measure, that measures electricity conductance in the soil. Is really good for making maps. And so you can make soil maps of electrical conductivity that in this region is associated with organic matter and water availability. But then notice that, for instance, this electrical conductivity is important and consistent in this field. This is field 6. But for field, the field 5 in purple, well, it doesn't work consistently. So apparently, what is causing a lot of this year-to-year variation on these responses to crops is basically weather-soil interactions plus the inputs that are happening. So the temporal consistency of the response zones to the same inputs across year was inconsistent, mostly due to the weather. And the spatial agreement between zones for the same year was higher as they share similar controlling factors. So year-to-year variability is much more significant than the variability that you can see for different inputs on the same season. So nitrogen and seed responses are highly dependent on water-related attributes too. So the maps that you saw early on when you fly over Champaign at landing, what is showing is that there is an impact associated with the hydrology that is happening underneath the ground. So some ideas on what to work on the future. We would like to compare several methods of defining these management zones besides the traditional site characteristics, I will say. So we are currently working on a paper on that. Incorporating remote sensing and real-time monitoring to gather more granular information would be very useful as well, maybe. I think especially methods that allows you to apply in situ as you are screening the field for nitrogen deficiencies might work. And then more advanced artificial intelligence algorithms that allows you to capture additional information. The main method that we used before was a random forest approach, and it has been, we compare many oftentimes, and it has been so far the most consistently reliable, I would say. So with this, I would like to acknowledge help of University of Illinois and the DIFM project, along with the support of USDA and the farmers. Currently, our research work group is very diverse. We work in a wide range of topics, but I thought this would be really interesting for you, and I'm looking forward to your questions. Thank you.
For your information. Any comments or questions from the audience you like to take?
No, I want to go with the Taiwan questions first. I have a.
So I see a couple of questions that were here from that are in the chat. So so the first one I got is, can this prediction paradigm predict specific diseases by its colors and other features? I think it's related a little bit with the question I asked early on. I think it can help, but depends a lot on the nature of the disease. So depends on the life cycle of the crop, the life cycle of the disease, and what is the kind of, I will say, damage that it causes. So if it is chlorosis or if it causes senescence, it's easier. Some other types are complex, as we discussed early on. So I think it's possible, but I think it requires additional information. So that's the first question. Second question that I got is, what factors are the most important when using data to predict zones in Illinois agriculture? So we discussed a little bit about those. So we are mostly using topographic variables. We are using electrical conductivity, but people also do soil sampling as well, sometimes more or less extensive as well to monitor the soil conditions. So those are the most common. And last one is, could you include will you include excessive details in management zones lower the overall efficiency? Oh, that is a good question. So there are a couple of ways to answer that. I think what I have noticed from the literature and from direct work from other people is that probably the impact is not worth the hassle, I will say, the effort put into defining them. And I will say, in reality, it's not the detail itself, but the uncertainty and how we are framing the problem. So, I think the idea of identifying areas that are more risky or less risky is more intuitive for the farmers, and I think it's a little bit more reasonable to set expectations, I will say, on the people who is going to be using the technology. And also, I think this type of trials can help us to gather a lot of information over time too. So I'm more optimistic, I will say. But what this work helps us to do is to think, start to think and ask different questions to move forward. Okay. So those are the questions I saw in the chat.
Nico, my question is more of a comment. You said something about this in your next steps, I think, and that
yeah,
many people that are starting to show use of remote sensing tools. I just wonder the opportunity to, for example, like you're combining DIFM with the research that you're doing.
Yeah.
A way to kind of cross-validate some of these types of systems. And is anyone actually doing research in that space, or are the tools kind of moving independently and no one at the interfaces are the tools giving similar answers?
Yeah, I'm very interested in working on that. So we have my plan will be to integrate some of these trials as they are right now or from the past, and look at satellite images from, for instance, Planet or any other source. I like the Planet ones because they take them very often. So you can target and see, you can pick a specific a big plot or smaller plot and track it over time and see in more detail what is the pattern that is taking place throughout the season. So I've been talking a little bit with one of our students here, with John, to work on that. So I think we can do it, and I think also that with other designs or other rates might be also helpful too. Okay, yeah, great question.
A follow-up question is, you know, a lot of the learnings we have are based on farmers that have the most advanced equipment and high levels of farm management integration. Are we able to make inferences that can help farmers that are more historical or how called?
Yeah, I would hope so. Yeah, because I think if, let's say that we have several hundred of these fields, we should be able to identify patterns. Like if you have this kind of history, if you have this kind of topographic features and some additional context that we can add, I think we should be able to come up with stronger guidelines for that.
Because we can know topography, and we can know soil types, and we can know weather. So
yeah.
So if you could couple that with some remote sensing, does it provide insights that could help more of a conventional farmer?
Exactly, and I think and I've seen this in other, I would say, research efforts in industry as well, is maybe they can try different designs. They don't need to do this full grid. That is, it's challenging to implement, and especially it's challenging to then harvest, aligning with the, I would say the hardest part is the harvest in a way. So I think that additional trials like that, plus other designs that are a little bit more flexible and that you can collect in many more fields even, I think that could be really, really helpful.
Thank you.